Hello and welcome back. My name is Corey and you're my rubber ducks for the evening, and this is the series of episodes where we are creating a programming language from scratch using C++, a terminal window, Vim is our text editor, and some fundamental tools such as Flex, Bison, Google Test, and ICU as our Unicode handling library. We have been, what number are we on? Number 95, I think is that what the number it was? Yep, episode 95. And we have been enhancing our opcode variety and making them more efficient. We know that we've gained about 10% in efficiency so far, and we are continuing along that. We figured out, I think last time or the time before, I don't remember, this is, once we figured out that, oh, this is the direction that we need to head, we've been having to go back and add more opcodes. And just to demonstrate somewhere here, I think, yeah, this is the list of opcodes. And whereas used to we had an add opcode, now we've got add SS, add SI, add IS, and II. So S meaning pull from the stack for the left-hand side, and I meaning pull from an index using an index location. Of course, if we can use index locations, that's much more efficient because it's less copies that need to be done. We don't have to copy something to the stack only to pop it from the stack in the next command. And when you push and pop onto the stack, that is, it's just even more work that has to be done. So, yes, that's what we're doing. And sorry, just thinking out loud. We've done all of these. I guess I wasn't thinking out loud. I was thinking very quietly. We've done a lot of these operations. There's a few more. So assign index. We know that we've got to pop an index location, pop a collection, and then have a value. Well, all three of those could be I's. So this one has 8 options, so that's going to take a little bit of work. Are there any others that are perhaps less work? We did period, we did index. Slice, again, it's going to be collection, begin, and skip. That's 4 possibilities that any one of them could be an index. And that means, well, to the power 4, that's 16 different opcodes. And at that point, it's like, well, could we make it a little faster? Maybe. We can. We'll think about that. But I believe get iterator is one that would benefit from an index. And we'll have to look and see how the iterators work again, because I don't remember. I wrote it, but it's been, if this is episode 90 some odd, it could have been any time in the last 3 months, because I've been putting out about a video a day. But we also need to go back and, for our cast instructions, if we fed it a string, we had not optimized that yet. So we need to go back, and probably for our prints as well. Basically, we added macros in the previous episode, and we need to make sure that everybody's using those so that everybody gets the same advantage. Or by everybody, I mean all of the incidences of what's the word I'm trying to say? All the different places where we use them. Yeah, that's what I meant to say. All right. So let's jump in. On the right-hand side, we will do our standard make clean, make test, watch. And on the left-hand side, we will say get log and show that our last commit was episode 94. That was the end of the previous episode. And if I say get status, the only thing that's there is a call ground output that I should probably just get rid of it, but I'm not wanting to delete it yet. But it's not part of the project code, source code. So anyway, leaving it for right now. That means nothing up my sleeves. This is 100% live coding. That means you see all of my mistakes. And yeah, the point is to do this live in front of you. And we're going to start off. Let's look at our, not our source, our include macros. Okay, we'll want to open that. Let's go ahead and pull our source opcode, our include opcode, and what else might we need? We might need let's go ahead and do our source program analyze, source program dump, source program execute. And I think I want to compare my source AST node binary. Oh, there's the ternary. We haven't done, well, the ternary is, we're not checking to see whether or not we can use. Okay, we could update, upgrade the ternary as well. But source AST node, let's do the unary. And the source AST node print, and I think there was one more, source AST node oh, we haven't done the while and the if else. Cast. Okay, we'll start here. And these are the opcodes that we created. Opcode find index, and we use that to find a left-hand side and a right-hand side. That's fine. So if we look at the binary, we'll see we've got something for the logical operators, but for how we do the binary, it just, in the case of an add, we use that macro to generate all the code fitting in the left-hand side, the right-hand side, and the four commands, opcodes. Yeah. And the and or use the logical op, the custom one that's at the top of this. Okay, so why are we pointing this out? Because the unary is, we use it here, unary op, but let's go back to macros and put it there. And you'll notice, ooh, do we do the return? I think for binary op we remove the return. So let's not put the return there. And we have this LHS and RHS thing. Okay, so up here, there, LHS and RHS. And now we'll do the find index. Oh, we don't need the LHS and RHS. So let's call that, instead of LHS, what, operand? This up here uses expression. but yeah, we'll call it operand. Okay, and then we need operand and index, and that will take care of all of that. And now yeah, all of that should be, I mean, the rest of it is, this part is the same as the binary. Let's see if, oh wait. This one needs to be saved, but we need to pound include macros. I believe we added that to the make file. All right. Unary up. No, unary op. Oh, and we need to give it this arrow operand. Yeah. Okay. And if it's this easy, well, that's a good thing. It gives us more time to work on other stuff. Yeah, all of our tests are still passing. That's a good thing. So I'm going to quit and see what our changes are. Git diff. We've got the macro that we added, and then where we moved it out of unary, in which case we were taking into account the string. So this is just this is a true refactor. We didn't add any functionality or lose it. We just simplified our code a little. Okay. And source. To use SI macros when compiling AST node unary. All right. Let's go back now to our set of files, and let's see what B9 has for us. So for our compile, here we do the exact same thing. So print, we need to pound include macros. And it will be this arrow expression. And instead of negative, it'll be print S and print I. Okay. What am I missing? Oh. Yeah, that's okay. What happened is what should have been expression on the unary or operand, it was hard-coded as this arrow operand, and it should have been is that right? Oh, the unary op. There we go. This sort of approach. So instead of this arrow operand, it should have been operand arrow compile. Of course, everybody who relies on this is going to have to be recompiled. And this is a fundamental one because it defines what our dash t is. But I mean our uinteger dash t is. But oh well. But that does simplify the code a lot. That's for sure. That's my theory. Anytime you have boilerplate, try to streamline where you use it. All tests are passing. That is good. So let's fix the macro one first. Git add, include macros, git commit and macro. All right, and now for the AST print, that's fine. Refactor to use SI macros when compiling AST node print. All right, we can go back to this and now go to the last one, which is the cast op. I had the right idea using cast. But it's really just a unary. And all that we need to do is pass in this arrow expression. All right, and now for this, from here to, or is it $ to the end? What do we want to do? We want to change cast op to be unary op. Yeah. And now I should be able to delete all of that. Macros. Getting rid of a lot of lines. It's always a good thing. Everything's passing. That's good. Cast. All right, 5 insertions, 32 deletions. Everything is done. Now, let's go back to this. And what did we talk about? We said we could do which one? I'm old and forgetful. Get iterator. Let's look and see how get iterator works. So I'm going to source AST node for the iterator. It's part of the ranged for. Yeah. And so collection is the word that we care about. The question is, well, that's just a break and continue stack. So But I'm wondering if we can do this collection get iterator s, get iterator I. Okay, that should be fine. So we no longer need to compile it. All right. So iterator next. Okay, so we're using the iterator next should only be an I, but let's get this working first, okay? So get iterator s, get iterator I. For now, that's what we'll do. Okay, and it's going to say it doesn't know what that is. That's because we need to start adding it. So get iterator s, get iterator I. Get iterator s, get iterator I. Of course, this had to be too long. Well, I guess it's right at the right length. And what are we? We're in the analyze. Get iterator s, get iterator I. All right. Which one is it? Which file is it complaining about? We'll come back to this. In the dump bytecode, get iterator y for. So for the s, it's just a dump binary. And for the I, and this is the execute. So get iterator. It's not a binary op. Is it a unary op? Unary op s, unary op I. Okay, that's fine. And what is it called? Let's go back to that. Oh, for the unary op s, unary op I, it's going to be called operand. All right, and I did it wrong. It should be collection without the not. There, I think that's right. So unary op I, that seems correct. All right. Now let's fix our compile problem. When we're compiling node ranged 4.cpp, making sure also I got everything. I got all the way through the, okay. So B11. Oh, ASC node string is not declared. Hey, okay. Just needed to get all of the right includes. All tests are still passing. That's always a good thing. Okay. I want to look at this again. What do we do? Once we get it, if we just told it where to write it, which index to write it to, no, that's going to make our command, well, it might work. Yes, I'm arguing with myself. What I'm worried about is we could just tell the iterator immediately what index location to store the identifier to, and that would remove a an instruction at that point, remove a poke. Because I can tell you what we're about to do when we're saying iterator next, we're going to give it the location and just say load it there and save it so that we don't have to poke it again. And then is iterator in, we'll just give it the location. Here's why. Our iterator is it's a special variable. We always have that. The iterator variable name. Let's go up. Is equal to, we feed in a string stream. Yeah, it's basically the memory location of this AST node. And you know what? Let's look at it. Where is that going to be? If I were to say cout this iterator variable name. Okay, we're going to see a lot of junk in here, but that doesn't matter. The point is to see it. Why does it look like this, or why did I do it like this? Because this is impossible to be a variable name. Yeah, that's why. It's impossible for it to be a variable name. Because variable names can't start with a number. So I knew that it would never overlap. All right. Let that reload. So then the question is, like I said, can we just give it the location of where it should go to? Yes, we can. We can say, moving that up. There we go. Now we can say index position. So that we can access it directly. All right. Now, in this case, unary_op will write . Unary_op will write unary_op. 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 Unary_op will write unary it's going to see it as an S or an I. But then we're going to say program add bytecode iterator index. Okay, so we no longer will need to save it, and our get iterator s will, instead of, yeah. So I'm going to remove the semicolon just so it can't compile. And let's see, where will this be? In our, first of all, let's go to number 4. Iterator s is actually, now it's going to be a plus equals 2, and this is going to be a plus equals 3 because there's one more byte than normal. Okay. Iterator s is going to be dump binary I and 2 i's there. Okay. And then get iterator s. What does peak do? Okay. We have to make sure that it is there. So let me just copy this. There. And now, okay. So I know that whoops. You know what? It's pretty much this, but it's not bytecode plus 1. It's going to be plus 2. No, it is plus 1 in the case of get iterator s. Stack check, and now we don't push back, we say stack at equals and now plus plus PC. Unary op s only increments by 1, but this particular opcode is special and needs to increment PC by 2 total. Instead of only, how about already? Increments PC by 1. All right. So now, get iterator s, we will tell it where to put the iterator. All right. And how about this one? For get iterator I, it will stack push back. Yeah, that's fine. We need to execute program check of 2 because it's going to be one further. The position is bytecode of PC plus 2. Stack check that position. Set the stack position as that. Already increments it by 2. But we need it incremented by 3. Oh, and there. Unary op I. Okay, now, so this will work. It's still not compiling all the way because we have a semicolon missing. That's intentional. Because now we need to go back so get iterator s and I will save it to a provided stack position. Do I have include opcode? Yeah. Now this will okay, so the question is, should this just be labeled I and I so that it's known that that's what they're doing? Yes, I'm doing that. And now, get iterator s is going to be get iterator si and I. I and I. Okay. I and I. Okay. All right. Now, si and I. Even though we're treating it as a unary op, then we're adding the iterator index. That's fine. Note we are unary op. I want to say, well, an additional there's an additional index. The additional index location is not treated the same as a binary op. How about as in a binary op or unary op? But unary op is the closest, so we will reuse its functionality here. That should be the word here. Okay. Now, so do we need to save the iterator variable? Nope, it's already there. Next, call iterator next. The iterator okay. So iterator next really needs to be underscore I, and it's the only option. Iterator next underscore I. And save the so that we can access them directly. Okay, and this will be, instead of iterator index, it will be target index, GET, this arrow, target arrow name. Okay. Now, iterator next is going to be II. Because we're going to say load the iterator, call the iterator, and poke it somewhere else. So it's going to be now program add bytecode iterator index, and now target index. Okay, so iterator next. We're going to fix this. Iterator next, II. Iterator next is now iterator next II. Iterator next II. Do we pop an iterator? No. The next at supplied index to calculate the next value, then store at second supplied index. It should be probably stack index, but that's fine. Okay, that's iterator next II. So iterator next II is now going to be +3. This in the dump bytecode, we dump binary II. Okay. When I call binary op II, right there, I get LHS and RHS. So let's use that. No, I don't want that. Where is this? So 930, go to the top. Are these just, oh, they're right here. All right, so let's do this. We've got a left-hand side index. We verify that it's there. And right-hand side index, verify that it's there. However, do we need to... We could call this iterator index. Iterator index. Iterator iterator index. All right, and then this one is target index. Target index. And then it's going to be stack of that. Instead of RHS, it's going to be target is equal to iterator arrow iterator next plus equals 3. All right. That didn't work. That's fine. Now that will iterator over and over. Is iterator end? We don't need, it doesn't need to look at the stack. It can be an underscore I. We're going to have to write this, but let's go back. Is iterator end underscore I? Is iterator end underscore I? So oh. What all does is iterator end do? Okay. Let's go back to this. Get back on track. So we get the iterator. We call iterator next, telling it where the iterator is and where the target is. We don't need to poke it in anymore because it's there. So is iterator end? That's the only thing. It's going to put something on the stack, but we can do it just pointing it at the iterator. Because what was on there first? Yeah, we poked the value into the target, and now we can just say is iterator end and poke it at the target index. Yeah, that'll work for at the moment. And now we can get rid of this poke. And then the rest is just a jump true, jump false. Okay. Make sure this, so we compile the code block, put a pop after it. push the iterator variable to the stack. We don't need to do that anymore. Load iterator, peak 0, jump to call iterator next. But call iterator next is we just give it a stack location. Okay. So we no longer have to push the iterator onto the stack. That's better. So we've got this is iterator end I that we need to write. Is iterator end I, okay, is iterator end I. Oh, that's... push a bool of is okay. I think I like that. Is iterator end I. And for that, and that will be dump binary I. Is iterator end I. What do we need to do here? Okay. So at the is iterator end I 941. Okay, at the very top, cast op. If I do unary op I, what will it do? It will get the index, check it, and load it into operand. So I think unary op I is what I want. And that's what it looks like. Yeah, unary op I. And then I should be able to do stack pushback a Boolean, where I can say if the val is a computed expression iterator end or error. And unary op I there. It does increase the PC by 2. Okay. Now, I think we are to a point where we can... Oh, 85. What is load iterator? Oh, yeah. Where was that? Get diff of source AST node ranged 4. Okay. Look at that. White space should never be there. There, it's gone. But what am I looking for? Load iterator. I mean, it's right here. What I should like talk to you and explain it. You're my rubber ducks after all. What's happening is before we had to pull up the iterator and then jump to iterator next. Call iterator next is that. And now iterator next is where we call iterator next, II. So what would happen before is load iterator, and what's missing is when you hit continue, when you say continue in your code, what should happen? Well, it should go to the, it should load the next iterator. So what was happening before is we would say, oh, okay, then I need to go to this spot where we're going to peek of the variable name, the iterator variable name. Remember, that's the one that's a memory location. And what do? We then jump to iterator next. So since this no longer exists, we can just jump directly to call iterator next. So pop our continue stack with call iterator next. Should work. See if that... Okay, we got through the compile. That's always a good sign. Now, whether or not the tests pass, that's another thing. Val is not. Okay. Program execute. Program execute. B6. Why? Because it's no longer called val. Unary op1. What does it call it there? I don't remember. Unary op1. Unary op I, and it's called operand. That would be why. Substitute the word val for operand on just that one line. Okay, they're not all passing. But they're mostly passing. Let's see what's happening. Line 1429. I don't think we've got our tests open. $14.29. It is indeed. Oh, it's a slice. And $14.95. I should just say if you dump P1, it should just dump the bytecode. All right, let's see what this is. We've got null val, null val, null val. That would be an A, num, and it should be this value. Integer 1 all the way up through 9, array 9, poke that into A. That's fine. Null val, null val. Integer 2. Oh, start, end, skip. Pull the slice. Get iterator si. That's not being... Oh, wait. S? Yeah. Oh, I say S1. What? I was saying 1 earlier, wasn't I? Oh, wait. No, wait. It's just running out of space. That's why. Okay. Get iterator S and put it into 1. Iterator next 1 and put it into 2, which is num. Is iterator end 2. And it will jump true with a pop. All right, that seems to be correct. So let's do some stuff, shall we? Let's put it here. And on our program execute, wait, did I just miss something? No, that's call func. Okay. There. All right, so now it's going to tell us the program count locations, and then we'll just scroll up and see what's happening. Did I forget something? Oh, I must have hit undo. I'm like, yeah, stuff isn't showing up like it's supposed to. There. All right, and so it's doing 1, 2, 3, 5, 7, 9, 11, 13, 15, 17, 19, 21, 23, 25, 25, 26, 27, 29, 30. It's dying at get iterator S1. All right, that gives me somewhere to look. First of all, it's SI. SI and II. You know what? Let's just make sure. SI is +2, II is +3, that's right. Dump binary I, dump binary II, that's right. Okay, so we call unary op S. And by the way, now it's gonna show SI1, II 1, 2. That's fine. Is iterator end 2. Jump if true to 45, otherwise print I 2. Pop the result of the print, jump to 32, which is iterator next. Yeah. All right. So we say unary op S. Unary op S, it says, is there something on the stack? If so, operand is equal to stack back. Pop it, and so operand is that, and okay, that's fine. And then I call execute program check to say, hey, is there one more opcode? And if so, the position is bytecode +1. That's fine. I make sure that that position exists. Stack fp plus position is equal to operand arrow get iterator using operand. This all looks correct. there. Just see if it gets past that stack check. No, we're not getting past that stack check. Is it dying before it? Yes. Okay. Position and stack.size. Oh, I should have said what FP was as well, but okay, we'll get there. Position 82, yeah, that would not be right. Why is it position 82? Position is bytecode PC plus I. So did I write the wrong position? No. Get iterator SI is just one. Unary op isn't doing anything weird. I'm calling unary op s, aren't I? Yeah, unary op s. Execute program check of 1. Yeah. Position is bytecode of PC plus 1. Just to make sure. That's an 82. That's an 82. I would say that both of those are very suspicious. Why is it 82? 82 doesn't make any sense whatsoever. And sorry, I thought I knew what I was doing. Evidently I didn't. Where's the dump bytecode? This is just a minor thing. Still not far enough. Yeah. Sorry. I was hoping I could make this look a little nicer. Either way, this is the problem of the moment, right? Why is it coming up as 82 twice in a row? See, it's 82 there. And it's 82 there. We know that it was dying after 30. So 30 is get iterator of si, and it's pointing it to 1. So get iterator of si is called like unary op s. And we're dying at the stack check because position is set. But why? Bytecode is obviously 1. Evidently it's not. But the reason is because unary op changes PC, and I'm using PC here. So I need to make sure that that I can check it. There's that. This can go away now. Unary op. Then I can stack check position. It's all in the order. And because I'd clicked in this window, it was frozen or scroll locked. All of our tests are passing. Yeah. Okay. Let's find those couts. There's one. Where's the other one? There's one. So what was the principle there? Always double check your assumptions. Pretty much. Oh, let's go back to our test. Why did I do it that way? Because I want to be able to look at this. This has a double thing. I wish I'd checked it before we had, because this is, I mean, it eliminated a lot of opcodes. Here we go. 2, 3, 4, 5 null vals being reserved. Integer 1 through 3, turn that into an array. 4, 5, 6, turn that into an array. 7, 8, 9, 10, turn that into an array. Then turn all those into an array. Poke that into A. That's 0. Pop. Get iterator of 0 and put it into 1. Iterator next of 1 and put it into 2. Is it at the end of 2? If true, if it is at the end, go to 64, which is past the end. If not, get iterator 2 and put it in of 2 and put it into 3. And 2, by the way, is iterator n. No, that's the result of iterator next. So get an iterator for it and put it into 3. Iterator next of 3, put it into 4. Is iterator into 4 true or false? If it is, go to 61. Jump if true, sorry. Go to 61, which is a jump back to 39. And 39 is get the next iterator. Yeah, so all of this is correct. Otherwise, 49 here is get the inner iterator. I like that. All right. Let's see what this diff looks like. Get iterator next, and is iterator end. That all looks correct. This all looks correct. Let's say add si opcodes for get iterator, iterator next, and is iterator end. (82 insertions, 59 deletions, and a whole lot more efficient, if you ask me. Whoops. Still bouncing back and forth between 4 and 5, but I know it's more efficient. All right. There is one thing that I want to test, And we saw last time, in fact, I'm just going to go ahead and run it here. If I run time build apps tang-s feed in fib.tang, we can try running it a couple times. Why is it slower today? I don't know. Because we haven't changed anything that it relies on. Where is my notepad? Just put it here. What I'm curious about now, and we saw that last time if we got rid of the singleton object pool, check. But we can't get rid of that. I know we can't. But what I want to do is I want to see if our include of garbage collected and our source garbage collected. Let's just go ahead and do our test watch. And what I'm curious about is, what if we've got ref and count. To recycle the object. What if we didn't have that? We've only got ref and count, and we no longer have recycle because I'm about to do something hideous. And that is in the make garbage collected, forget that. What if instead so it's no longer from the singleton object pool. And I no longer have the recycle thing. And now it's gonna ref. Oh no, wait. Ref is fine. Recycle is what's going away. So here it would be ref. So now we're not using the singleton object pool at all. I'm just writing so that which means we won't have the mutex. In this case, I know this is because this was testing the singleton object pool. Whoops, I'm on the wrong window. If I run this test, yeah, all the tests passed just fine. How does this normally run? The reason I'm asking, that's a lot of output. I know it normally gives me a truncated thing, but that's not... it ran in 6 milliseconds. With that much output, I would have expected it to have taken longer. That's what gtest brief -1. Okay, that's fine. Now, if we time Tang-s, give it Fibonacci.tang. You know what? This one's the middle one. Okay. Just so I know it's not a fluke. I know oh no, I don't even have to do that. Git stash. Unfortunately, because it's garbage collected, it's gonna have to do a lot. So let's do J8. Compile a lot faster. You know? Between these two, it might have been faster to just never even worry about the object pool thing. All right. All right, well, that tells me something that I can definitely be thinking about. And just for the moment, I git stash pop, git, I'm going to undo it, include and source. Okay. And let's update our documentation. And I don't remember what our last, so 94. So we're on episode 95. Okay. That's J8. All right. And just making sure, yep. Origin master. Did I already tag this? No, I did not. All right, and now, of course, one of the last things we do is just kind of see where we are. 12,600 lines, and 3,700 lines of comments. Okay, almost 2,000 blank lines, but hey, who's counting? Again, line count does not reflect quality or anything else. It just kind of lets me know how much am I keeping track of. And that, I think, if we can figure out a way of reducing the number of computed expressions or garbage collected values. Okay, so we can probably follow up on the garbage collected idea and remove that, remove the singleton object pool dependency. We can probably do that. It would be probably fastest to use a singleton object pool and not have to worry about thread safety. But because of the way that I want this, or I intend on using this language, it's very possible that there could be multiple threads accessing templates that are being created. This is the idea, is that this could generate a lot of templates and have multiple, think serving a website or something, simultaneous users and everything like that. So there would have to be the thread safety, and hence the mutex. But by just using new and delete, well, yeah, maybe a shared pointer. Maybe we could just go all out and just use a shared pointer. And then we wouldn't have to worry about the rule of 5 stuff. It would just exist. Well, think about it. But we want to cut down on the number of times we have to make a call to, or copy those the garbage collected values. And let's see. Anything else? No, I mean, that's it. Of course, other things that we can do in terms of efficiency, yes, we can look at the slice and have it, but like I said, that's going to be, there's 16 instructions there. We still haven't dealt with the ternary. That might be it is an optimization we could look at. But I think we've done just about everything. This one was a big one, and this one really, in my opinion, made our byte code that is compiled a lot cleaner, and removed a lot of unnecessary work. Anyway, that's what I think. So, all right, having said that, I think we're at a good stopping point. We're almost at 2 hours. Sorry. So, hey, sometimes you got to do this in exploring and refactoring code. But hopefully you're enjoying it. Thank you. Have a great day. And bye.